So adding, so the good news here, again, there's really only two operations that we talk about with vectors. There's adding, which works exactly the way you think it's going to work. And then something called scalar multiplication, which we'll get to in just a minute. There's really no such thing as subtracting. But there's a way around that we'll look at in just a minute. So let's start with adding, because it's you talk about common sense and like doing what you think you're going to do. It's doing what you think you're going to do. So I'm going to use those same two vectors that we had yesterday, the vector v -5, 6 and vector w 9, 4. Take a wild stab, and every single one of you are going to give me the right answer. I can tell you that right now. But if I said add these two vectors together, what do you think you would do? What do you think? Of course, your answer is going to be a vector. But what do you think you would do? Even if you don't know how to do this, what do you like? And I said, I'm not going to tell you how to do this. Just do it. What would you assume you would do if you're going to add those two things together? Don't be afraid to be wrong, because you probably won't be.
Would you like add them separate from being done and once you get the total each and just add those together, or just add them all together?
Yeah, so you're gonna kind of do them separately. You're gonna add the x's. That's what you said the first time, right? You're gonna add the x's, get that number. You're gonna add the y's, get that number, and you're done. Because your answer is going to be a vector, right? So your answer is still going to be something comma something. So you just add the x's. So I'm going to do the work kind of over here on top. So it'd be -5 plus 9, and then 6 plus 4. And you just do that little bit of arithmetic. So -5 plus 9 is 4, and 6 plus 4 is 10. And that's it. That's your answer. You're done. Like, that's it. So just you combine the x's, watch your signs. You combine the y's, you watch your signs, and then you're done. All there is to it. Now that's the only thing I want you to be able to do. Now it's going to get a little more complicated because we're not just going to add two vectors. That's a bit too easy. But when we go to the next step, we're going to do that on the next page. But I do want to show you. I'm not going to make you do this on an assignment or on a test, something like that. But I want to show you graphically what it means to add a vector. Okay. By the way, your answer, here's one more vocabulary term for you. When you get your answer, whenever you're combining vectors in any way, your answer is what's called the resultant vector. Okay. Fancy word for an answer. That's what it is. Okay. So what does it mean graphically to do this? Well, we have this thing called the parallelogram law. I didn't know that, but here's what we do. And I went ahead and drew these arrows on here just so, because I suck at drawing straight lines. So I went ahead and drew this up here, but here I'm going to label these things and show you what's going on here. So if I take v plus w, notice this vector here is vector v. Because notice v is -5, 6, and if I go -5, 6, that's the point, -5, 6. Okay. But here's the trick. Here's why this works graphically. Normally, we would graph 9, 4, vector w in standard position, like over here somewhere. This right here, in fact, is vector w. But notice, if I move vector w, instead of being right here, if I shift that to the end of v, it's something called the head to tail method. If I kind of just pick this vector up and set it down on the end of v, that's what it means graphically to add the vector. Because notice, if this is my endpoint of v, negative 5, 6, if I go right 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, and up 4, 1, 2, 3, 4, look at the point I'm at. I am at the point 4, 10. And sure enough, so this vector here going from the origin, kind of in the middle of this box, this vector is v plus w. I'm going to highlight that vector just so it kind of shows up a little bit better when I scan the nodes and get it in the folder. Okay, so that is your resultant vector. In fact, it doesn't even matter what order you do the vectors in. So I did here v plus w. You can also do w plus v. Notice this vector here on the right-hand side, this is also vector v just kind of picked up and moved to the end of w. So that's vector v. So the order when you're doing it graphically or algebraically for that matter, the order doesn't matter, but you're always going to get what's called this parallelogram. And then the resultant vector is going to be the diagonal of the parallelogram. Okay, kind of interesting. Again, we're not going to make you do this on an assignment or a test, but I would like you to be able to at least kind of recognize the setup of it, so that if you do see it in upper level math class, if you go on to a math class in college next year or something like that, that at least it's not completely foreign to you from there. Okay, so let's do 2 other examples real fast. Just on straight up adding vectors. Okay, so example 1, given vectors 5, negative 2. I'm calling them vector A and B, letters don't matter. But if you have vector A is 5, negative 2, and B is negative 1, negative 4, I'm going to give you just about a minute to tell me what your resultant would be. Again, all we do is add the x's and add the y's. And then I'm also going to draw this on the same graph just so you can kind of see it in real time, what it would look like. And then we'll kind of leave the graphs after that. So what would the resultant be if you add A plus B? Watch your signs, but again, combine the x's, combine the y's. What do you got? If you combine the x's, what does that become? Something in the chat box. Yep, 4, negative 6. And it is a vector, so we want to use that, those little pointy brackets. Yeah, 5 plus negative 1, 5 minus 1, which is 4. And then negative 2 minus 4, negative 2 plus negative 4, negative 6, perfect. If I were to graph that, and I'm just going to graph it on the same graph up here. I can't do it in pink. So if I were to graph that, and that same using that same parallelogram law, I would go vector A is 5, negative 2. So 5, negative 2 is right here. Let me see if I can draw a straight line. You're about to laugh at me because that's not terrible. I've done worse. And then I'm going to do -1, -4, -1, 1, 2, 3, 4. So that would be vector B from the origin. But if I'm adding these, so that's A and that's B. So if I'm adding these, basically what I do is I'm going to make this vector, I'm going to shift it to the end of this. You do the same kind of motion. You do the same left, right, up, down. So if I start at the end of A and I say, okay, B is left 1, down 4. So left 1, down 4 would be right here. Or I do the opposite thing. I go to the end of B and I do what A did. So I go right 5, 1, 2, 3, 4, 5, and down 2. And notice I get to the same place because math. So the resultant vector would be, again, that diagonal from the origin going down. And notice that point right there is, in fact, 4, -6, which is what we just found. Okay. Let's do one more. Again, I'm going to give about 30 seconds. I'm not even going to graph this one because my graph's already kind of a mess. So I'm not going to bother graphing this one. But give me the answer on adding T and M. What would your answer for that one be? So combine the X's, watch your signs. Combine the Y's, watch the signs. And we get, I got something else in the chat box. Oh, that was from the first one. So this one ends up being 4, -7. It's always funny. I didn't plan for that to happen, but when I write questions, even though I'm using different numbers, I get numbers kind of stuck in my head and they kind of happen automatically. Anyway, but again, just combine the X's, combine the Y's, adding vectors, that's all there is to it. Okay, but it's not very exciting. Like, it's kind of cool when you're graphing them, but it's not very exciting. And let's face it, we're going to have to do some more things with vectors than just adding them together. So let's take a look at the other operation that we have. So how can we, again, there's no such thing as subtraction, but what we are allowed to do with vectors is we're allowed to multiply by any constant. So we call that, the name for that constant, and you might have heard this in physics, is a scalar. A scalar is just a number. It doesn't have direction. It's just a number that kind of makes a vector longer or shorter by that factor. Okay, I'm not going to go through the whole graphing part of this, but if you multiply a vector by a scalar, like if you multiply it by 2, it's going to be twice as long. If you multiply a vector by a half, it's going to be half as long. So it's just a multiple of a vector, making it longer or shorter by that same factor. Okay. But algebraically, what we can do is now we can do problems like this. So again, I'm going to use these same vectors that I've been using for the last day and a half, -5, 6, and 9, 4. Now I can do a problem like this, where I can do 3v plus 2w. Where that 3 is a scalar and the 2 is a scalar. You can think of it like a coefficient. That's all it is. Think of it like a coefficient. So if I write out what that is, so I would do 3 times the vector -5, 6 plus 2 times the vector 9, 4. So basically just plugging in the vectors for the letters. And again, if you look at this should kind of ring bells from your algebra days of, even though it's out of parentheses, we can still just distribute because that's all you do. So if you have a 3 times a vector or any number times a vector, we're just going to multiply that 3 into both of those guys, and the same thing with the 2. So this would end up being negative 15 and 18 plus 18 and 8. And then once you got it distributed, once you got the scalars in there, then we just add them like we did on the first page. So your final answer here, again, just combine the x's, negative 15 plus 18, which is 3. 18 plus 8, 26. And that's it. Graphically, you would do the same thing. Like I said, I'm not gonna, because you need a big piece of graph paper for 26 and all that stuff, bigger numbers, but it would work the same way. So I'm gonna give you guys a chance again. See if you can do this. Mind the order, because we can be in any order, right? So see if you can figure out 4w minus 5v. Now, when you set this up, I'm not gonna do the whole thing. I'm just gonna kind of set it up here for you. So it would be 4 parenthesis, bracket 9, 4 minus 5 bracket negative 5, 6. So when you're distributing, especially on the second one, make sure that you distribute the negative sign as well. That way you don't forget about it and go from there. So I'll give you a minute, see if you can figure that one out. And if you think you get the answer, you can stick it in the chat box. You can just multiply each individual term. And then once you get your 2 multiple vectors, your 2 other vectors, once you finish multiplying, add the x's, add the y's, final answer. Morning. How the answer looks like. Christopher, that's not quite what I got. I'm checking my math because maybe I made a mistake. But your x number is off by a little bit. So check your arithmetic on that one. Close. Oh, yep, that's better. Okay. That's it. So again, multiply, distribute. All it is, distribute. 4 times 9, 4 times 4. 36 and 16. Plus, and again, the reason it's plus is I'm multiplying by the negative through there. So once you multiply by the negative, then we're just going to start adding the vectors. So I think that's an easier way to go about doing this. So negative 5 times negative 5, positive 25, negative 5 times 6, negative 30. And then just combine x and y's, 36 and 25 is 51. Chris had me scared. I thought math was broken. And then 16 minus 30, negative 14. That's your answer. Any questions so far? We're going to the next we got three things on this, three more things on the same page. They're not really operations, guys. That's all the operation. That's literally, well, that's a lie. That's not all the operations, but it's all the operations we're going to cover. There is something that we call the dot product of vectors. That is useful in some physics applications, like if you're determining work, like if you're pulling a cart or dragging something up a hill, something like that, then you can calculate the work using what's called the dot product of a vector. And then there's something that is not in high school pre-calculus at all. It's called the cross product. That's something in a little bit higher level mathematics. When you're talking about torque or induction current, stuff like that. But again, that's not high school level at all. Okay. But as far as what we're doing, adding and scalar multiplication, that's going to be the extent of what we're going to be doing with vectors. Okay. So a couple of the loose ends. A unit vector is just what it sounds like. If you guys remember our old friend, the unit circle, we called it a unit circle because it was a circle with a radius of 1. We just call the radius 1 for the heck of it. A unit vector is a vector that has a magnitude of, you guessed it, 1. Okay. But the reason we like unit vectors, again, they often have applications in physics and things like this. So if we're given whatever vector that we have, we like finding a unit vector in that same direction. So whatever random vector that we're given, we can find a unit vector. So in that exact same direction, basically overlapping the given vector, but it only has a magnitude of 1. So like, if we go back to our same two vectors we've been using, V and W, all we need to do is find the magnitude of those vectors. We did that yesterday. So that was in yesterday's notes. Remember, the magnitude is just the square root of the sum of the squares. So we talked about that yesterday. So I'm not going to go through the whole process, but this would be the square root of 25 plus 36, which is the square root of 61. Don't even care about the decimal. So to write the unit vector, this is all we do. We take the vector itself and we just divide each piece by the magnitude. Remember, that's our notation for magnitude. So the unit vector here would just be saying, for vector V, it's -5 is the X over root 61. And then the Y is 6 over the magnitude, root 61. And that's our unit vector, done. Don't overthink it. If you know the magnitude and you got the vector, we can write the unit vector without even doing anything. Because it's just the vector itself, each component, divided by the magnitude. Same thing for vector W. Find the magnitude. And again, we did that yesterday. That was just 81 plus 16 or root 97. So to write the unit vector in the direction of W, we just write the whole vector, each piece over the magnitude. That's why I'm putting these echo pieces on these same notes, because it was just like, there's not much to talk about. It's just, all you got to remember is for the unit vector, it's just the vector divided by magnitude. It's all it is. No tricks. The same, it's always the same sign, if it's negative or whatever, everything's the same, just the components divided by the magnitude. The other super easy thing that we talk about is something called IJ notation. Okay, this is not as common these days as it was when I was your age. I'll be completely honest with you. But if you take physics, or if you take any kind of STEM course and they talk about vectors, a lot of times science people like using this what's called IJ notation. I personally think it's kind of dumb because I just use a normal vector. Why not? But people like IJ notation, so God bless them. So all you do, I and J are called the standard unit vectors. So I is defined as the vector 1, 0. And J is defined as the vector 0, 1. So in other words, this is just going up 1 unit. I'm sorry, going to the right 1 unit. So it's just on the x-axis 1 unit. And then J is just going up 1 unit on the y-axis. That's all it is. Okay. But what this means is we can now write any vector that we're given as a combination of I and J. Okay. And I even wrote this out. I was going to say it out loud, but I wanted to put it on paper. Don't overthink writing these things. It's literally whatever the vector you're given, you put the x times I plus the y times j, and that's all it is. So if I want to write v -5, 6 as ij notation, you would write -5i plus 6j. These two things mean the same thing. It depends on who writes the vector and what kind of mood they're in, but it's just a different notation. And you can write any vector in ij notation. You know, like when we come up here to this scalar multiple, I could have written this 326. You could write that answer as 3i plus 26j. It's the same thing. Or 51i minus 14j. They all, it's just different notation for the same vector. Nine, 4. Do I need to ask? What would that be? IJ. 9i, 4j. I didn't even know who came up with that, honestly. Like I say, I've always thought IJ notation was kind of dumb, but I don't know why we use it. I've never gotten a good answer. All right, last thing, and this one isn't quite as kind of silly as IJ notation, but the last thing we're going to talk about is going backwards. So we spent this whole last couple of days about, you know, having a vector in center position. So we know the starting points at the origin, we can make an operation with it. We can find the magnitude, we can find the direction. But how about if we go backwards? So how about if I tell you have a vector that has magnitude of 12 and direction angle of 140? Well, I know what that looks like, right? I can draw a picture of that. You know, if I got the direction angle of 140, remember center position, so it's in quadrant 2 somewhere, and a magnitude of 12. So that means it's kind of over here. So that would be my 140-degree angle. And then the length of that vector would be 12. But what I want to do is I want to take that vector and I want to be able to find my x and my y coordinates, basically. I want to write it in component form. I want to find the horizontal component and I want to find the vertical component. So if you want to write that same vector instead of with magnitude and direction, you want to write it in component form. Here are your two formulas. Okay, remember notation. So it's the magnitude of v times the cosine of the angle theta that you're given. That's the horizontal component. And then magnitude of v times sine theta would be your vertical component. And that's it. This does need a calculator, of course, because sine and cosine, stuff like that, make sure you're in degrees, just like everything else. So if I want to find m, calling it vector m this time, then I just take my magnitude, which is 12, cosine of the angle, cosine of 140. And then the vertical component would be 12 sine 140. And you stick that in a Desmos, again, make sure you're in degrees, and you'll get negative 9.19 and 7.17. And you can use some common sense on this, folks, because when you get these numbers, notice my x is negative, my y is positive. That makes sense because I know my vector is in quadrant 2 based on the angle. So we're good. Okay, magnitude cos theta, magnitude sine theta. All there is to it. I'm good on time. Yep, right on time. So last one, magnitude 40, angle 312.4, weird angle, who cares? I know it's in quadrant 4 somewhere. Like over here, ballparkish, with a magnitude of 40. I want to find the x and the y. Plug and chug. Forty cosine theta and 40 sine theta. And those will come out to be, when you put them in Mr. Desmos, 2697 and negative 29.54. And again, that makes sense because I'm in quadrant 4, so x is positive, y is negative, and we are good. Okay. Guys, I know I put a lot of information to you guys in the last couple of days between all the vocabulary and stuff like that, but none of it's super kind of crazy. Just like yesterday, I will have a completed copy of these notes up in the folder for today, along with the video. I'm gonna stop recording right now, so it doesn't take too long to process.